Perfect.
Yeah, so I hope you can see the screen. Uh, all right. Okay, so it's my pleasure to be talking here. Big thanks to the organizers for putting together such a great program, and also to all the participants who've given such great talks so far. It's been a lot of fun. Okay, I want to talk about stuff that we've been working at Xanadu, and even before I get into the details, I really want to acknowledge this is a team effort. The effort from a great team, both at Xanadu and also our academic partners. And um, I think we really had a blast working on this problem. So I'll talk about a blueprint for a scalable photonic quantum computer. And when I say scalable, I really mean the full thing. So it has to be a full fault-tolerant universal quantum computer. Okay, so this slide is from Google, and I think it really captures the situation very well. On the x-axis, we have the number of qubits, and on the y-axis, we have some worst case qubit error rate. And the thing to take home from this slide is that getting to fault tolerance is a marathon. We are 5 or 6 orders of magnitude away from where we need to be. And of course, this is from Google, but for all other architectures, a similar picture holds. So there is a long, long way to go. And if we are really far away from where we need to be, what matters most is how quickly we can move, how quickly we can increase the number of qubits, bring down the error rates. And of course, this has motivated many people to look at many different platforms. And as far as scalability is concerned, all platforms have major challenges ahead of them. I want to give an example. This is really just an example of some of the challenges that we might see. It's representative from superconducting qubits, but also for other platforms, there'll be similar challenges. So these are the really nice superconducting chips that we have. And in principle, it's possible to scale up the number of qubits on the chip by just stamping out more qubits. But the problem is here. It's in the wiring that gets the signal to the superconducting qubits. And in fact, right now, the number of qubits you can put into a cryostat is limited by the amount of wiring that you can put into the cryostat. And these are microwave signals, so you really need wiring, really good wiring inside the cryostat and outside the cryostat. And also there are serious challenges to manufacturing many, many wires. Okay, so all I want to say is that the case for which platform will be the first one to get us to fault tolerance, that case is not closed. And I think here, photonics provides a very nice advantage as far as scalability is concerned. Okay, why? This is because photonics is native to communication. This basically means that if you can make one very good chip, then you can combine many such very good chips together and build a big fault-tolerant quantum computer. And also, photonics provides us with really nice flexibility as far as encodings are concerned. So you have flexibility about how to implement a qubit in the state of light, and also on how to put many qubits together into a logical qubit. And also, since we are building upon decades of hard work from silicon photonics, there is low noise, there is low crosstalk. All these things put together means that we will have better overheads, which is very important for getting to fault tolerance. And finally, we have the icing on the cake, which is that photonics gives us room temperature computation. And this means basically that you can use processes that are already available in fabrication today. And this is really a big boost to scalability. Okay, within photonics, how would you go about doing computation? And the way to do it is measurement-based quantum computing. This is because photons are flying qubits, unlike matter qubits, which are on which you would do circuit-based computation. With photons, you need to do measurement-based computation. So a quick primer on measurement-based quantum computing. In usual circuit-based computing, what you would do as well, you would have state preparation, followed by entanglement that is generated by the gates, and finally measurements. But with measurement-based quantum computing, you would take all the entanglement and move it to the front of the circuit. So you start from an entangled resource state. And with this entangled resource state, you can perform computation. If you want to perform computation on one effective physical qubit, then you generate a 1D cluster and then perform measurements sequentially on the cluster. And eventually you are able to implement gates on this one physical qubit. You take many of these 1D clusters together and stitch them across each other. And then you get a 2D cluster, which effectively acts as n physical qubits. So a 2D cluster is universal for measurement-based quantum computing. But if we want to have error correction and move towards fault tolerance, then we need redundancy. And one way to get redundancy is to go into the next dimension. So then you have a 3D cluster state. This is how you would perform computation on n logical qubits. Okay. And there are different ways of doing quantum computing with photonics. And the two dominant ones right now are the dual rail qubits and the continuous variable GKP qubits, which is the Xanadu approach. So in dual rail qubits, you have a qubit encoded into two modes of light. If a photon is in one mode, this is state 0. If a photon is in the second mode, this is state 1. You can have superposition of the photon being in one mode or the other, and then you have different superpositions of 0 and 1. At Xanadu, we followed a different approach, which is the continuous variable approach. These approaches have their own advantages and disadvantages, and I'll get to these in a moment. But before that, let's talk a little bit about what the continuous variable plus GKP approach is. This figure is from the really nice work from the group of Akira Furusawa, where they generated a 2D cluster. Yeah, this is a 2D cluster because if you cut along the length of the cylinder, then you basically have a sheet. And this is the sheet that I showed earlier. It is universal for quantum computation. The nodes of this sheet are squeezed light sources, which are generated with these OPOs, which are then connected through linear optics and then stitched in time with time delays. And finally, they perform homodyne measurement to check that you have the correct state. So experiments have been done to generate such states. The challenge with these architectures is that you need to attach GKP qubits to each of these nodes deterministically. By deterministically, I mean that if the computation requires, and the computation does require a qubit to be attached to one of these nodes, it has to be with unit probability. So this part is a little bit of a challenge, but the advantage with this CV cluster state, continuous variable cluster state, is that all of these optical elements are Gaussian. All of these can and have been implemented at room temperature. So there are pros and cons of the CV quantum computing approach. Okay, and I mentioned GKP qubits. We've had some very nice introductory talks, but a super quick reminder. In phase space, a coherent state looks like a blob, a squeezed state looks like an elongated blob, but a GKP state looks like pieces on a chessboard. And GKP qubits are natively loss tolerant, because if there is some error on some of these pieces, as long as the error doesn't move you out of the chess box, the chessboard box, then you can come back to the original state. So GKP's states are really good qubits, and they're also very good t-shirt art if you're into that stuff. But coming back, okay, so the dual rail approach versus the CV approach, we have advantages of the CV approach, which are that you can do computation at room temperature. So squeezing, linear optics, delay lines, homodyne detection, this is all room temperature. So you can do room temperature computation. You have native loss tolerance thanks to GKP qubits. But there were still some challenges in using the CV GKP approach. So these were the challenges that we set out to overcome, and that's what the architecture is about. Okay, so If there are questions at this stage, I'm happy to take them. I'm around 11 minutes in. I can put in a couple of minutes for questions.
I haven't seen questions in the
Okay.
chat, so.
Thanks. Then I'll continue and take the questions at the end. All right. Okay, let's begin with the architecture. So as I mentioned, one of the big challenges with photonic quantum computing is generating these GKP qubits. And this was a big problem till very recently, but a string of great works has shown that you can use Gaussian boson sampling devices to generate GKP qubits. And these Gaussian boson sampling devices basically comprise squeeze states, linear optics, photon number resolving detectors. And if the photon number resolving detectors give you the correct click pattern, then you know that the remaining output modes have a GKP state in them. Now, this is a non-deterministic process in the sense that the correct click pattern only emerges once in a while. So maybe one time out of 100 or one time out of 1,000, you'll have the correct click pattern. But when you have the correct click pattern, you know that you have a GKP qubit. So this is a non-deterministic GKP source, which I represent by this simple rectangle. The problem with this source is that it's non-deterministic. The probabilities are low. These probabilities need to be boosted. And this can be done easily with multiplexing. So the idea is that if you have 100 different GBS devices, each of which fires a GKP source 1 in 100 times, you make them all run in parallel and route the output from the correct GBS device to the output of a multiplexer. So this increases the probability, but it cannot get us to unit probability. You will still have cases where none of the GBS devices fire, so you actually don't have a GKP state that is generated. What do you do in these cases? We show that every time there's a no-show, you replace this qubit with squeeze light. And this still allows us to carry on with the rest of the architecture. So now this multiplexer becomes our hybrid qubit source. It shoots out pulses of light. Each pulse is either a GKP state with some probability or a squeeze state with the remaining probability, but we know which pulse is which. Okay, we have our qubit source now. Let's talk about generating the resource state. So a 3D resource state, which is what we need for error correction, we can generate this in 1 temporal and 2 spatial dimensions. Let's talk about the temporal dimension first. So we have a hybrid qubit source shooting out pulses. Some of these are GKP qubits, some of these are squeezed light sources, and you make the pulses talk to each other on a simple interferometer. Well, this gives us a 1D cluster state. So we've turned a qubit source into a source of a pulse train, which is a 1D cluster state. And this cluster source I represent with this triangle and a circle. Okay, now we have a 1D cluster state. We need to go to 3D. So the 2 extra dimensions come from putting many of these 1D cluster sources together on a 2D lattice. And this 2D lattice can easily be done on a planar integrated photonics chip. So with these gates, you can generate entanglement between the cluster sources. You can have cluster sources and qubit sources together. This pattern generates a Rausendorf lattice, and this completes the generation of the 3D resource state. Okay, let's put everything together now. So we have a state factory which generates the GBS, which generates the GKP states. We have multiplexers which boost the probabilities of generating the GKP states. And we have this computational module, this chip that I just showed, which can stitch together our qubits into a hybrid resource state. And the hybrid resource state has either GKP states or momentum squeeze states. Okay, this hybrid resource state, you can perform computation on it by just performing homodyne detection, which can also be done at room temperature on the chip. And just by changing the phase of the homodyne local oscillator, you can perform measurements in different bases. So this is all that we need to do to perform computation, change the phase of the local oscillator of the homodyne detection based on measurements from previous time steps. And this completes the description of the architecture. Okay, so as you can see now, we have a planar architecture as well, which works for the CV plus GKP qubit approach. We have inexpensive state preparation because we don't need any unit probability GKP states. We also have inexpensive Clifford gates because earlier approaches required that every single gate consumes a GKP qubit, and this is really expensive. By swapping out some of the GKP qubits with momentum squeeze states, we actually have inexpensive Clifford gates. So well, putting it all together, now the continuous variable and GKP approach looks quite promising, but we're not done yet. There's a lot of follow-up problems, some of which we are solving, some of which we will solve. And the first one is that we need to tailor this architecture even more to the hardware. So far, we were talking about clusters that were stitched together using CZ gates, which involve inline squeezing. This is a problem, but we are close to completing an architecture which is all passive. So on the chip, there is no inline squeezing, everything is offline. And we need more sophisticated noise models. This also means you need much better CV simulators, which is a really hard problem, but we are close to releasing in open source a CV simulator where you can play around with your favorite circuits that have GKP qubits, and this will be out in a few weeks or a couple of months. We need better GKP state preparation. This is the most expensive part of the architecture, and we're working very hard on making it better. From the error correction side, we need better encodings, better decodings. So we need not only bosonic codes that are tailored to the noise, but also qubit level codes that are tailored towards the noise that comes in the bosonic qubits. And hopefully we can have really good decoding, which captures the entire homodyne data that we are recording, not just the qubit bin values. And also, since everything is light, these qubits move really fast, so you need faster decoding procedures. Okay, and for all these hard problems, you should come work with us. We are hiring error correction researchers, quantum optics researchers, and also there are internship opportunities for grad students, for undergrad students. So yeah, and also academic collaborations are welcome. So please come work with us. All right, I'll just summarize the architecture. So we have a concrete, which is a planar architecture, which is scalable in the sense that we can really go to very large number of qubits. And this architecture allows us to do CV photonic quantum computing. It uses concatenated GKP codes. So you have 2 layers of protection, which means lower overheads. And also it's really scalable because the cryogenic requirements are minimal. So it's only that the GBS devices require any cryogenic conditions. Everything else is at room temperature. Manufacturing is much easier. And also, since we are using photonics, everything is small planar modules that can be networked easily. Okay, so this is our architecture. With that, I'll welcome questions, and thanks everyone for your attention.
Thank you very much for your presentation, and we have still a lot of time for a nice discussion. So there were a few questions raised in the chat, some of which I wonder whether you just answered them. So the last one was, you still need superconducting photon number detector to generate GKP states, so your platform is not totally room temperature, but I think it was just on your last slide, if I'm not mistaken.
That's right. That's a great question from Kiro. Thanks, Kiro. The only part that needs cryogenics is the photon number resolving detectors. Currently, this is all in cryogenics, but also there is a roadmap for moving from cryogenics to room temperature, because there is nothing that prevents photon number detectors from actually being at room temperature. So yeah, at Xanadu, we are also thinking quite seriously about this. If you head to our blog, then you'll see a long technical discussion about what are the possibilities of going to room temperature photon number resolving detectors. But right now, 100%, we still have some cryogenic requirements.
Thank you. So let's look at another one. what is the main advantage for using the GBS in generating the GKP states over other methods such as photon catalysis?
Yeah, I think the quick answer is the rates. So we want to generate very high fidelity GKP states at very high rates. And whenever we are looking at all the different approaches, then GBS devices seem to have been many orders of magnitude better as far as the generation rates are concerned. So this is why we are looking at GBS devices right now. I should also mention that at Xanadu, our near-term architecture is GBS. So we have a GBS device that is up and running in the lab that anyone can access on the cloud. And basically, this is a technology that's good today, but getting much better very fast. So this is another reason, more a technological reason for choosing GBS devices.
So while discussing GBS devices, there is another question, which is the state generated when you don't make a GKP state still useful of that device?
Yeah, I think, and also the second part of the question is really nice. Is it also non-Gaussian? Yes, it is non-Gaussian. And so we do hope that there can be some way to use it, but so far we've not been able to find a way to use it. So currently we're just throwing away the light. We've really thought long and hard about this question. So if you're interested, yeah, we should chat and figure out how to solve this.
Great, sounds like an interesting project. Does Xanadu use the Clancy nil or the sum gate syndrome extraction for the GKP code? Can you comment on the feasibility of each of these schemes in the quantum optics setup?
Perfect. I think this is a great question. So in the end, we will have a situation where the entire cluster is stitched together with these GKP states. So basically, we are using a teleportation-based scheme to perform error correction. This happens automatically as you teleport into fresh GKP qubits, and hopefully with this, so hopefully with this, the error correction question is solved. And then the second part of the question is, what's the feasibility of these schemes in quantum optics? So we really think that teleportation-based schemes are the way to go, because then you just start with these simple planar chips, which allow you to construct the 3D lattice. And then you're performing computation via teleportation. We are performing GKP error correction via teleportation. So all of this happens really smoothly. Yeah, I hope that answers the question.
I hope so too. Thank you for explaining. So there are more and more questions coming up. So silicon photonics still has some loss. Could you give some numbers on how many effective single 2-qubit operations you can do coherently with current technology?
Right now, I don't think I have the numbers. So this is really an architecture that we're proposing. So also we think that it is not entirely clear what would be the final platform. Silicon photonics is definitely very promising. The GBS devices that we have will be based probably, or currently are based on silicon nitride. And these have a lot of loss, but the loss is coming down really quickly. Yeah, as far as numbers are concerned, I don't have numbers at the top of my head, but yeah, we should chat a little bit more offline and figure out exactly how to find these numbers.
Thank you. Looking forward to hearing about the numbers in the future.
Thanks.
So we still have time for discussion, and I find it very interesting. So what is the main limitation of clock speed of your device? Would that be the detection rate, photon pulse repetition rate, or something else?
Yeah, another great question. In the end, the device is limited only by homodyne detection speeds, which are really very, very fast. So gigahertz to tens of gigahertz, maybe even more if the electronics permits. Of course, this means that you have to bring everything else in the computer to the same rep rates. This means that you need to do a lot of demultiplexing of your detectors to make them function, of the PNR detectors that generate the GBS, that generate the GKP states. You need to somehow boost the PNR detection rates as well. And this can be done with demultiplexing. This can be done by just improving the technology. So overall, in the end, the limitation will be homodyne.
Thank you. Sounds challenging having the fastest quantum computing device in practice.
100%.
Yeah, maybe we have still time for one more question. Where are these photon number measurements being performed? Are you planning on performing them on the chip itself?
Perfect. Thanks for the question, Rajveer. I think this is something that has not yet been finalized. Currently, these are all offline, so all the detectors are in the cryostat, but then we are working on really low loss interconnects from GBS devices to the cryostat so that everything happens low loss. But eventually, I think this would be a really nice project to undertake. So we are thinking very seriously about having also the photon number resolving detectors on the same chip where the Gaussian boson sampling is performed. So yeah, I think both these routes are open and both these sound quite exciting.
So if there is no more questions, I would really like to thank you again for your interesting presentation and everyone else for being in this session and all the previous speakers for their exciting sharing of results.